So you all can see the whiteboard now, right? I don't know why I cannot see the whiteboard. Oh, okay. It just came up. The whiteboard is just something to play with. As the lecturers were trying it out, after a while we decided this is not a good idea because students will just be distracted because everyone can contribute. For you all to play, you all can play lah, but we will be using this for class. I have a better system myself. Hi Ikai, lecture is not starting yet. We will start at 3:05. We will watch and see. Give people some time to come lah. Maybe a bit of delay. For now, you can play with the whiteboard. Jeff, if you're on the WhatsApp group, then you will see we have discussion already. Utah, no decision yet. We have a strong preference to continue, but if there is such a decision, then we got no choice but to comply. As a university, our class slightly different. Yeah. But the latest update we have is that the ministry heads are meeting again today, so they will discuss this further. So far, there have been a lot of changes in decision at the last minute. So we will wait and see, and we will not jump to do things too fast when we don't need to do lah. Yes, Lingus Warren, definitely our one of our priorities is that students are able to graduate. I mean, that's the whole point we run the course. So we will try. Don't worry about that. Okay, we will be starting in a minute or so, but I'm still trying to handle certain students that cannot log in. So give me some time. I will close this whiteboard. Let's get this started. How do I close the whiteboard? Okay, if you can hear me, type yes in the chat. Okay, that's good. Can you all, if you can see the slides, say yes, I can see the slides. Just type the word slides. Okay, that's good. Let me see how many we have. We have 79 currently, pretty good. I have a few of the classmates who are having issues with logging in, but I can only do one thing at a time lah. So let me just announce there. Okay, let us start the class. I'm not sure who keeps starting the recording, but I will start the recording myself now. I don't know, because I think some people have been clicking start recording, stop recording repeatedly, so I don't know whether there'll be multiple recordings that come out at the end. Okay, so I will start the recording and we will go and let's see how fast we can progress. There will be no attendance taken because we are not actually in class. So we will not be taking attendance for the whole period of time that we are doing e-learning for this trimester. There will be no bar list generated for this trimester as well if you have read the latest mail master that was sent out this afternoon. That doesn't mean you shouldn't come for class. Even attendance not taken, what is taught in class is still useful. So you make your own decisions. You are adults. I'm not going to try and chase you all. I give you the opportunity. Up to you what you want to do with it. So let's look at our topic 3, end of arm tooling. So we have talked about the end of arm tooling previous to this, but this entire section here is about, oh, Angeline, a little unclear. Are you using headphones or are you using a speaker of your phone? Angeline, are you using headphones or speaker of your phone? Okay, headphones, is it still unclear? Thanks everyone, but I'm asking Angeline specifically. Okay, it'll be good, I think, because if the rest are saying that it's quite clear, because if I make this louder, it's going to be peaking already. Okay, so I'm increasing the volume on my input. Is this better, Angeline? And if this is too loud, please let me know now. Too loud, Yeah, that's why I think there will be some type of what we call peaking in audio thing. So sorry, Angeline, I will have to put it down. I would check whether you have a volume setting both on your phone as well as a volume setting on your headphones. Okay, so apologize if it's slightly unclear, but I think yeah. Okay, so anyway, 310. Let's see how much we can go through. We have been talking about end of arm tooling. Let's talk specifically about suction grippers, and we have a chapter exactly all on suction grippers because of how versatile they are and how useful they are. So the slides you already have, but I will just put this up here so you know what I'm talking about. So these are the different types of suction grippers. Not all of these are robotic suction grippers. The one on the left, you probably have it in your bathroom. And they are very useful, simple to make, cheap, and yeah, you can use them to carry many things. For example, you can see on the left hand side here, a vacuum layer gripping system. This is so that you can carry bricks in a particular arrangement. Then you can put them down together like that. So you can carry construction material, heavy things, and we have a lot of suctions which is being used. So that's called a suction spider, handle and separate porous sheets of insulation. Obviously, it's easier to imagine using it for glass, but on the right hand side, you can see that you're using it for metal pipes actually. So this is all possible, And when we talk about suction, don't just have the idea of the simple suction cups you use on your bathroom wall, because those are simple. You can only stick on the bathroom wall. If you've tried to stick it on a plaster wall, you will know it doesn't work, right? But when you are providing external power for the suction, there's a lot more that we can do with suction. So here's suction spider on the left hand side, and for a molded part that is not a flat surface, you can see how you design the suction system so that it can handle a non-flat surface. Okay, so an overview of your vacuum system. So you have your generators, your mounting elements, filters. Some of these things you've already talked about in Dr. Lee's system, so I wouldn't want to go over it again. You should already be familiar. Okay, so let's look at the suction gripper itself. So obviously, anytime you have a suction gripper, again, this is not a simple one you use in your toilet. So you need some type of power supply, which is your vacuum line. There's a pressure switch. There's the angular freedom of movement. So basically, it allows it to tilt. You need exhaust, your vertical freedom of movement. You can have an interchangeability where you can actually change the cups. The holding force itself is generated at the suction portion, and there is a sensor to see whether it's contacted or not. So generally, when we talk about suction, we are using air as the medium. And the air, basically, when you create suction, there must be a pressure difference between the interior of the suction cups and the surrounding air. The point of the cup is you create a seal. And that means that the atmospheric pressure will press the lips of the cup against the workpiece. And then the suction cup creates a boundary of a pressure zone. And this means that basically you are holding this up using air. Okay, it is the air pressure itself which is holding the material. And this works even with very heavy material. The advantage here is that you can build up the holding force, and if your workpiece is soft and flexible, you're not deforming it too much. Of course, there are certain which you may, so we will talk about that later. If the material is slightly porous, then we won't draw through this. But of course, if the material is very, very porous, then the suction can overcome the porosity, and then it will pull through. Okay, so for suction cups, as you use smaller suction cups, this actually means that the gripping force becomes higher. And you have a formula here. You don't need to memorize, but this is basically relating the force with the area and your various coefficients and things like that. Okay, your coefficient of deformation, which is depending on basically how soft or how deformable your suction cup is normally between 0.9 to 0.6, and the rest of the parameters are here. So your pressure, blah blah blah. Okay, so there's a safety factor, which is always very important, of course, for engineering systems, as well as an efficiency factor, where sometimes there's slight amount of leakage. Okay, so these are the force conditions with your vertically moving suction cup, and you can see where the force actually comes from. The air below the workpiece is the one that is pushing and actually carrying. So that's why when you're using suction cups, effectively you are carrying the item using air. Okay, so yeah, and then all the different things which are listed there are according to your formula. So the holding force of your suction pad depends on the effective diameter and the condition of the workpiece, as well as how many suction pads. So obviously you can design one suction pad, but for larger workpieces, the easiest way actually just put a lot of different suction pads. So if you are doing what we call horizontal pickup, then this is the equation. I think you can see my mouse there. And for vertical pickup, then things are slightly different, because for vertical pickup, you have to consider the friction coefficient as well. And the friction coefficient here is the friction coefficient of the material of the suction cup with the material, which is not so much of an issue for your horizontal pickup. Okay, so there are a few numerical examples here. So you have your masses, okay, and all your pressure, number of suction pads, your coefficient, and your safety factor. And based on these numbers, this equation, if you need it in finals, it will be given. Then you can calculate, oh, this is the diameter. So this is the diameter that we need for our particular suction cup in order to fulfill. Okay, so yeah, if we are using vertical pickup, which is the other formula, which includes your friction coefficient, then you will need 12.5 cm rather than 8.85 cm. Okay, so the formula themselves are the same except for the additional coefficient. If there's such a question, then you will need to know how to do it. Okay. Oh, cannot see the mouse. Okay, sorry, I just saw that. If you cannot see the mouse, then there's another possibility. Give me a minute. Pen. Mouse pointers, pen. Okay, can anyone see a pen moving around on the screen? No, Okay, but can you see if I circle this, the red circle? Oh, so you cannot. Okay. So this is a Linux thing. Then my cursor is not seen as a member of my screen. Never mind. I will draw it as necessary. I just need to remember not to save it. So basically, between horizontal and vertical, the same equation. This is the friction coefficient, the one I'm circling here. And so when you calculate without, you get 8.85. When you calculate with, you get 12.5. Okay. So now, if you have questions for me. Because I'm actually looking at my slides, I'm not so much looking at the chat unless I'm asking a question. It's okay to unmute just to say, excuse me, sir. Okay, you can interrupt, no problem. Then your voice gets to be added to the recording for your friends to hear. Okay, so if you have a question, don't be shy to do that. Yeah. So let me switch back. Let's talk about what is the vacuum that is needed. Okay, and it depends basically on the volume flow, how much air you are evacuating per unit of time. And this volume flow generates the vacuum, and this generates the suction force. So how much, okay, where is this? Okay, so the workpiece material is the principal factor for the required volume flow. And depending on your these are just typical values. It's not a list of values that you die must follow. But if you have various sizes of suction pads, then if you have from that, this is the area on to the next of it, and then from there is how much volume flow, either in your SI units or in your crazy country which nobody else follows units. Okay, so how do we achieve the vacuum? Then you normally use about 70%, which is about 0.7 bar or 0.3 bar in terms of absolute pressure. So your fine, high, ultra high vacuum, each of them actually have a very specific meaning in terms of the range of vacuum that is being generated. But yeah, you just need to know that there are these limits. We are not expecting you to remember what is fine, what is high, what is ultra high. In your assignment, however, if you are doing, then you must explain a bit more. Okay, so how do we get these vacuums? There are various ways. You can see the A, B, C, D here, which is either your rotary pump, your vacuum generator, the adhesive suction cup, which is the one that you use on your car or on the wall, and your piston suction system. Okay, so we will go through this. Wait, I am doing something here. Okay, so for a vacuum generator, it provides a particular level of vacuum using either pneumatic or electric actuation. And these ones are basically normally used to just quickly generate the amount of vacuum that is needed. This is used when basically these are so-called mobile, when you don't have a supply of vacuum, you don't have a supply of compressed air, then you might use this. Alternatively, if you need to boost, meaning you need much higher than what your general supply has. So vacuum pumps can give you high vacuum, low operating costs, and also a lower noise level than other systems. But the pump themselves is not as cheap. And that means that you have to basically what you are doing with a vacuum pump is you are recreating the big system, but only for your mechanism. Okay, so your typical vacuum generators, your vacuum pump and your ejectors can give you much higher total vacuum, but the volume that they can generate in terms of moving the air is not so much in terms of your suction capacity. So then your vacuum blower has a much shallower curve. Okay, so this is the single stage ejector working on the Venturi principle, and you supply your compressed air. When it goes through the nozzle, then it's accelerating and compressing. It's accelerating and compressing the air. Once it has passed that nozzle, which is B in the diagram, then the accelerated air is expressing. So through that, you are actually forcing your air to be drawn through D. Okay, then your C is where the air goes out. So as you increase the speed coming through A, you're actually pulling more air through D. And this is where you have your vacuum generated. Your vacuum generated is whatever you connect D to, and C is where your exhaust comes out. So this is a single stage ejector. You can have multi-stage ejectors where your D goes to effectively multiple ejectors. So as shown here, and your single input for your A, which is your compressed air, pulls in multiple inputs for D. Okay, so otherwise the principle is exactly the stage. This is quite commonly used for industry. The good thing is it's compact, it's quite light, and the vacuum generation is very fast. Okay, you just supply it to compressed air and it works. It works quite almost instantaneously. There's nothing moving, no flexible part, so there's no like rotary whatever. Okay, everything is static. The only thing moving is the air itself. You have no heat generation, unlike things which are motorized or electrical. Actually, to say no heat generation is not accurate. It's very, very low heat generation compared to other methods. Okay. Okay, I see there's some communication. Someone wants to go toilet. You want to go? Oh, need to wait until break. Okay lah. Toilet break. I will stop I'll pause the recording. Actually, no, I better not pause the recording. Let's leave it. Okay, toilet break, 2 minutes, go run. You are at home, so you shouldn't be very far from toilet. What type of GIF you putting? Waliu. Hi, Cheng Yang. Welcome to class. We are halfway through. Okay, yes, too late. Sure fail already. Oh, that's fair enough. Do you need more time, Jinghao? Okay, it's been 1 minute. I wonder if he's running or not. Yes, Prasaf, I think I started the recording. I hope the recording works and you will be able to download. Hopefully that. But for those of you who have attended, once you listen like this, most likely just reading through the slides is faster. Most of you reading will be faster than watching video. Yeah. Oh, regarding the practical, I will post this formally in the WhatsApp group, but we are on a wait and see mode. We are hoping that first week of April we can reopen and we can do all the practicals. So until you do the practical, you do not need to submit the report. Now, if worst case happen and somehow there is more spread, then we will have to reconsider. There are a few options, but I will discuss that only after 31st of March. We wait for our government to decide what is going to happen, and we also need to see what is the spread of this COVID-19. Okay, if the COVID-19 spread has been controlled, everyone social distancing very well, nobody go to the shop lot and spread to everybody in their kampong, then I think 1st April we can start resuming classes. It's good. If the spread gets worse, people are mixing around with their friends, then potentially all the way to final exam we are stuck in this situation, then we will see how to do the lab. Okay. Wait for government is bad idea, but unfortunately government makes most of these decisions. Whether we like them or not, whether we voted for them or not, they are still the government, so they will make the decision. Okay, and that's all I will say. I also don't want to get arrested because I'm a lecturer. I'm not commenting on anything else. Okay, so we will talk about the practical later. Let's continue our lecture. Yes, we will talk about this. Okay, no problem. Okay, so these are your advantages of ejectors. Let's just go next slide. Okay, so in this case, you have a shut-off valve, which means that you do not need to cut off your air, right? So if you can see from 4 there, that's where your compressed air comes in, and the rest of it is basically just a single stage ejector. And as long as your valve, which is in number 1, allows the flow of air, no problem. But as soon as you turn the valve, and this valve of course can be turned electrically or whatever, depending what's your design, then you can see that the compressed air is no longer generating vacuum. In fact, it is now pushing whatever is attached to the suction cup, your workpiece 6, it is now being ejected. Okay, so this one has a shut off valve. Okay, you can, when we are looking at vacuum generators, you can put them in a series effectively, and what this does basically is it increases the amount of vacuum that you are generating. Okay, quite simple. This is a solenoid actuated suction cup, and this suction cup basically, most of you would have seen in some people's cars, you stick the suction cup to put your handphone or whatever it is you put on your screen. Those suction cups is not the simple one where you just push it in, because that doesn't generate enough suction. When you're pushing it, you're generating suction by forcing air out. Okay, but most of them have some type of lever where you push it in first to force some air out, and then you pull a lever which deforms the suction cup in order to generate more vacuum inside. So in this case, you can use a solenoid, so electrically operated. What this will do is it will pull this up, and by pulling this up, it's generating more vacuum here. That force is generating more vacuum here, which means your vacuum pressure from the outside, the one you have more carrying pressure. Okay, so this is an example of a vacuum circuit, and this is things you are very familiar with, how we can provide the air for your vacuum circuit. Okay, so you have your pressure switch and your filter, and then in number 2 there is the actual ejector itself, which will generate the vacuum for your suction cups in 7. 8 is basically just a distributor where the same vacuum will be supplied to all the cups, so that all of them can do suction at the same time. So this is like your spider array of vacuums. Now, this is a fairly standard circuit, not a problem. What happens is that if you have multiple cups, then you need to consider your tubing diameter, because your tubing diameter controls basically how much suction each cup, and it depends where it is on the tree. So if you have so the tree is shown here. If you have a certain diameter for your main supply, then every time that it branches, you need to make the diameter smaller. The factor is about, I think, the factor is about 1.42 every time you branch. Okay, and so this is the same design concern which you see when you are looking on top at those central air conditioning systems, and you will notice that the diameter, or basically the cross-sectional area from the supply is big, and then it gets smaller and smaller as it goes to the exit. And this is so that in this case it's not vacuum, it's basically pushing out the air pressure, but it's the same principle that the air pressure is inversely related to what's the rate of flow. Okay, so when you are looking at suction cups, there needs to be a factor of 1.2, and it gets smaller and smaller as you go towards the leaves of the tree. Okay, so with these basic things that we understand, let's look at how we use these suction cups for various applications. Okay, there are a lot of ways to use your suction cups. Oh, I see a question. As I have mentioned earlier, for symbols, what sort of symbols? Wen Zheng, right? What sort of symbols are you talking about? So there's a question. It says, do we need to memorize the symbols? What sort of symbols? Sorry, which symbols? Oh, the pneumatic symbols. Let me switch back. For this type of thing, no, these are not things that come under the design things. The questions for these sections will be under either calculation or more likely in your memorization questions. Your circuit design wouldn't be including all the different types of vacuum. Okay, except if the vacuum is just your final end effector lah, which is just the thing which is right at the end, in which case you will not actually need to memorize because that will normally be provided in the question. Okay, so no need to worry about that. Any other questions? Now, I'm not sure why the recording keeps stopping. Is anybody playing with the recording? Yeah, because definitely recording was running just now, then it has stopped. I just started it and it stopped again. Okay, so be careful what you touch on the screen. I'm trying to record. If no record, then sorry about that. Well, you have the lecture slides. So let's look at the different applications, the ways to use suction cups for different applications. Yeah, so we need to consider whether is, especially F&B industry, there's different requirements. Temperature resistance, because obviously the material of the cup, some of them are not super temperature resistant. If you are above 70 degrees Celsius, this is normally a special case and you need special materials for that. For below zero, also basically it's hard to use suction cups because the utility of suction cups requires that they are able to deform. And as you decrease temperature, it becomes much harder to get our rubber-based or whatever material we are using, PVC-based, to deform reliably. So yes, I see recording has started. Yep, hopefully it's working. Okay, so this is a small selection of major types of suction cups. Before you ask me, no, I'm not asking everyone to memorize all 11 of this and reproduce them. Okay, but there are many different suction cup shapes and designs. It is entirely possible that so I'm not asking to memorize, but if I reproduce, let's say, oh, this is a bellows suction cup, this is a lifting suction cup, I can give you the drawings, for example, and say, hey, can you comment what's the difference? Okay, and this type of question is no longer testing, do you remember? Okay, but your understanding of the section itself, where you can say, oh, yeah, this one should be more useful for this and that. So it's more of your understanding, not your memorization capability. Okay, the other concern we have is that eventually, not in the near term, we want to move towards more open exams, maybe things that you can do online. And for those, we can no longer get things that you can quickly Google. Okay, so we are trying to design more and more for questions which test understanding rather than questions that test memorization. Okay, this is not just this subject. You would have seen it in basically every subject you take. So a bellows suction cup is, okay, so you all can read this yourself. And because of the design, it can work for different types of heights. So if the height differences, some minor height differences, this one can help. Okay, and if you use small dimensions of this type of suction cup, is suitable for thin materials. The problem with thin materials is if you have a very huge suction cup, the material itself might deform inside the suction cup. So you need small diameter cups, and bellows suction cups are quite useful for this. The pleats are, let's see, okay. So these are the pleats. Okay, and if you have a large number of pleats, sometimes you need to give a support string, because then this thing can be, it starts becoming like a spring in and of itself. So you need to harden it if you have too many pleats. Okay, these flat suction cups, these are what people normally call suction cups. They are suitable for non-porous, flat and slightly curved surface, and they tend to give the highest vertical forces. These are the deep suction cups, which are normally used for round surfaces, profile sections, basically things which will fit in like this. Okay, if you use for a flat surface, then there's a lot of pressure on these areas, and that's what we call rapid wear. Not a very good thing. Okay, your ribbed suction cups are suitable for flat and unstable surfaces, and you have ribs across the mouth of the cups, which means that these are more resistant to lateral deformation when material is pulled in this way. Okay, it's very useful for vertical surfaces because the ribs help for friction. Okay, so when you see the ribs here, these ribs here, I can imagine that when the cup is being actuated, that this would be deformed this way, and so the ribs will come into contact, and this will provide your increased friction. Okay, because now it's in contact once it is engaging the suction. Okay, so the other one, okay, so virtually 100% of the effective suction area is maintained because once the material contacts here, then this one cannot deform anymore upwards. The more rigid design means that you normally have a larger size without a spot plate, but if you have any sort of curve in your workpiece, then cannot do lah. Basically, you need it to be quite flat for your rib suction cups. Okay, there is a cellular rubber seal which allows to, so the seal is at the edge of the cup here. Okay, it's not good for applications with vertical workpieces because then this seal becomes the point of failure, but it helps to give a good seal. Okay, for this type of, I won't read it off, you can read it yourself. Okay, oval suction cups are useful when let me see, when you are doing long or narrow or workpieces where it is not rectangular or squarish in shape. They can also be used for large grippers with a lot of different suction cups, like your metal-based plates. The good thing about this is that you, in one dimension, it can be quite narrow. Okay, so if you only have a small area to stick to, then this is the thing that can benefit. Okay, your double lip suction cups is effectively one suction cup inside another suction cup. We call this the sealing lip and the sealing ring. So this gives a lot of elasticity, but if you are close to the maximum load, then it might your suction cups may have quite a bit of movement. Okay, as the load is split between this and this, between this and back again. Okay, so for self-adhering suction cups, these ones are not connected to any vacuum source, and these are the ones that you typically use in your room or whatever. This is the important point here. If there is leak, it fails. Okay, naturally. So they rely on 100%, whereas all the we had previously, small amounts of leakage are okay because the vacuum is consistently being generated. We use a hand lever to break the vacuum, and as the cup is pressed, then you displace air and a vacuum is created under the suction cup, but it is very hard to define because the deformation force can vary widely. Okay, so these are normally not used industrially. Okay, your lifting suction cups is where you have this piston here and the suction cup, and if you have adhering, then we will lift this cup up. Okay, so once a workpiece has adhered to the suction cup, because of the piston system, the suction cup itself is moving up, so you could be lifting the workpiece using this piston itself. This means that you can have 1 degree of freedom less on your robot arm or whatever you are using. Okay, this type of suction cup is used to handle tin sheets and things like that. Okay, so it will look something like this. You can even have the manual version of it. Okay, oh, I see there's been some comments. What is going on here? Sir, during my internship, the machine they use as suction cups, they pick up ICs in -45 degrees Celsius. Yes, definitely possible. Just like it's possible to have suction cups in much higher temperatures, but the material design of those suction cups, it needs to be fairly specifically done. And in particular, what you're picking up it's not heavy duty. When you say ICs, I don't know whether you're picking up the individual ICs. I think more likely you're picking up a bank. If that's the case, then I mean the mass is still not very significant compared to some of those that you saw in the introduction slides in terms of what we can carry. Okay, Kwan Ming, thank you for the video. I won't watch it now. Obviously, having lecture. And Sheng Yao, the midterm results, I plan to release it on Friday. That is still the plan. Even work from home, there is no difference to that plan. Okay, so wait for Friday lah. Today is still Wednesday. Okay, so continuing, if we want to evaluate the various types of suction cups, then we have to see what are the differences in terms of, this how much vertical or horizontal force you can use, and that makes a difference in terms of what cases we can use it for. So this table, which you can see, is basically measuring for various designs, your A, B, C, D there, whether it's very good or ideal or suitable or not applicable. Okay, depending on which criteria that you are looking at. So as you can see, like for example, your bellows, it is not applicable for if you want to transmit a horizontal force, because obviously it will give way. It can only transmit vertical force. And if you have a residual volumetric flow rate, then not really applicable as well. The rest can be applicable, but some are more so than others. Okay, so if the aim is to find how much force you can transmit, and depending on the residual flow rate, this involves the relationship between both the shape, material, as well as the surface of the workpiece. And we say surface properties is not just about material. More important is the shape and the roughness of the workpiece. Okay, so this is one of the design constraints that not constraints, the design decisions that you have to make. So your type A's are relatively large in flexibility, so it generally can be used for most applications. Type B has very high vertical forces because of the spaces. Okay, you can see all the. Okay, where's my? Okay, you can see all the spaces here. So then you have basically very high vertical forces, depending on your vacuum, of course. In your Type C, you have a double seal, which means it takes up quite a bit more space, and effectively the diameter of suction cup is the weaker one, which is the one which is internally. Okay, and Type D, there's no geometric stability. Obviously, if you try to use this Type D and you go vertical, then it's not going to work. It has a very large elastic vertical stroke. Its basic advantage is it's cheap and easy to design. Okay, so your freedom of movement of your suction cups is how free they are to move. So obviously with your bellows cup, it is basically not constrained at all. And at the different levels of how we design our suction cups, then you can design it for freedom of movement. For example, if you look at number 4, longitudinal freedom of movement, basically you can go up or down, and this is because the suction cup design itself supports this. This suction cup has freedom of movement in one particular angle, which is this angle, this number 5, and you can design for this. Okay, freedom of movement is not always desirable and it's not always undesirable. It depends very much. So when will we want, for example, an angular freedom of movement? Is when we have workpieces with contours on them, and we're trying to use a spider array of suction cups. So you can see how the design here helps such that instead of if you were not able to bend in this way, then you will only have one suction cup, which is carrying the entire workpiece. This suction cup cannot, and this suction cup is not even on the workpiece. But because you have what I have circled on the right here, therefore you are able to have two suction cups with full contact of the workpiece, and this makes it easier to carry the particular workpiece. Okay, so having some freedom of movement is good if it's freedom of movement in the angle that is beneficial for your application. Okay, if your suction cups are deep, I've mentioned this already, but this is just to show, if your suction cups are deep in terms of the depth here, then it can adapt both to a convex and a concave body. Okay, whereas a shadow one finds it difficult. Okay, if you have vacuum gripper with very large freedom of movements, then you can see that the workpiece, even in different heights, in different orientations, you can still get a good grip, okay, on the workpiece. So this can be desirable as well. Okay, so this effectively a bellows, which with sleeves. So your bellows means that you have your pleats here, but it's also a sleeved design, sort of like some of you have these cups, which you don't want to use the cups when you go outside, you want to save plastic, then you have these rubberized cups, and this is how they collapse into each other. This means that you can have a design, this is the full extension, but you can also have, if the design calls for it, a compression here. Okay, suction cups numerous, please. Normally used in the food industry. One of the unique things about the food industry is simply that your food ingredients are not always the same shape or size, unless you go McDonald's, in which case everything is exactly the same shape or size. Okay. Oh, I see a question. Wenchuk, if you have a question, I'm not looking at the chat while I'm doing the lecture, so it's good you unmute and just ask the question. Okay, so the question here is, what is the advantage of Type C suction cups? From the evaluation section, it seems to be the downside. Okay, let me go back to that particular slide. Where's my slides? I'm a bit lost. Is it this one? Oh, I know. I see what you mean. This one. Okay. Yeah. So this slide. Okay. So for this slide, yeah, basically these are the main disadvantages. So when these are not a problem, then this can be used. We have actually mentioned this a bit earlier here. Where is my slide? Okay, let me just go back to the slide here.
The double lip.
This one, also the double lip. So the benefit here is that it has a lot of elasticity. Okay, so this is the main thing. What does that mean here? Basically, this is like a double cup. Okay, which means that if you have a very uneven surface or something which is not very well defined in your problem that you are trying to solve, then this gives you a bit, okay, I can handle quite varying things, right? Whether this overcomes the disadvantages, the main disadvantage is there's a lot of wastage in terms of space design, because you must recall a lot of these cups are not used as a single cup. So you have multiple cups going together. So space becomes a big issue. If that's not a problem, for example, you don't need that much lifting force, then these cups are fine, and it gives you a lot of flexibility and robustness. Okay, so let me see where. Okay, so we were here. Yeah. Okay, so in some special cases, if you have tin foil, for example, the more suction you give, then you can imagine that there will be a problem where the fall material itself will deform. Okay, so something to consider. Okay, this one has a workpiece control activation of the suction air. Basically, what we are trying to achieve here is that the suction cups which are not covered, for example this one, if it is not covered, then it should not be giving vacuum power here. Okay, why? Because this is wasting energy, and if there is a free exhaust here, you are effectively lowering the amount of vacuum that is being supplied to the left one and the center one. Okay, so if you equip your suction fast cups in such a way that it's only when they contact with the material, and then that sends the valve up, and the contact itself means that the suction activates, then this one will not activate. Okay, the circuit one on the right. Okay, so this is a circuit diagram when you have a suction head fitted with your vacuum efficiency valves. Okay, which are basically unidirectional. Only when it's in contact, then it will actually draw on the vacuum power. Okay, here what you have here is when you want to activate the vacuum. In A, you have an actual electrical sensor, and when it senses that you are there, then you can activate. In B, you put the sensor not within, so integrated means it's within the cup. External means it's maybe on your robot tooltip, but it's not within the cup. You can have a vacuum sensor valve on the suction line itself. So C is quite interesting because basically that physical contact is the one that opens up the vacuum, and okay, now we can begin the suction. D is the slightly more high-tech one where your inductive sensor senses the material and it activates the vacuum when you are in contact or close enough to your metal material. Okay, so this is how we can activate based on the proximity of the material. So these are sensor based, whereas the previous one was mechanical based. Okay, so these are effectively proximity sensors which supply an electrical signal to activate them. And once you want to activate the vacuum, you need to consider that, of course, the handling that device, the height is changing. Then once the workpiece has been reached, meaning that you have reached what you are trying to pick up, then we want to activate the vacuum. So this will trigger the vacuum by actuating your control valve, in which case, yes, now your force 2 valve, let's say, it will move to the other position, then the vacuum will enter, and then, okay, you get the suction. Okay, so in summary, wait, let me see, am I summarizing? Yep, I'm summarizing. Okay, so in summary, when we are doing system design, we need to consider what are the type of suction pads, the type of cup that we use, and what type of mounting elements that we can use on top of the cup. How do we connect the cups to our system? What's the hosing? And as I've mentioned, you need to consider the diameter of the hosing. In particular, how do we distribute the suction? Okay, because we namely need some type of array. How do we generate the vacuum? And this is determined by how much volume you need to move, as well as how much suction power you need. And then this is where you have the control part of it. What are your solenoid valves and your vacuum switches? Okay, so if your workpiece is steel sheets on a pallet and your surface, so when you have all of these considerations, okay, you know this is how you define your problem. Okay, this is your maximum width, your maximum thickness, this is the weight that you have to handle. Then you can also take the information for the handling system itself, which are using a gantry handling system with this acceleration, this cycle time. How long do you need to do for pickup, for release? You need to calculate the weight of a workpiece. So based on the dimensions we give, we are looking at the worst case of 2.5 m times 1.25 m, blah, 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 and you have your density. Okay, our mass 61.33 kilos. So this is not like a formula, it's just volume times density. Then we already know what the holding force of a suction pad is, and so we decide, are we going to carry it horizontally the entire time? Is there a need for verticality in how we carry? So if we are looking at the horizontal, then this is the theoretical holding force that we will need. Obviously, you need to put a safety factor. You must note that the acceleration of the system must always be added to gravity, right? And this is because the worst case scenario is that it is moving up and your gravity is added to the acceleration. When you're moving down, actually it's gravity minus acceleration, but then no problem. If it can carry while moving up, moving down should not be an issue. Okay, so if you have a horizontal suction pad, then you have to consider what happens when your force is horizontal. Okay, and if your force is horizontal, then you have slightly different. Okay, the difference is, where am I? The difference is here. Okay, and in our example, you can see is 1008 newtons, where this was 1003. Okay, so the effect of that friction coefficient, it becomes a bit more of an issue. Okay, then if you have your vertical and direction of force vertical, then you will see that your friction coefficient actually applies here on the mass side, okay, rather than just on the acceleration side. And this is the worst case scenario. And this is not something that you need maths to tell you. Obviously, if you're holding it in this form, the vertical form, so your workpiece is like this, then this is going to be the worst case scenario. Okay, so yeah, if you are trying to select, then once you have calculated what is the holding force that you will require, then we can see the suction force, that you need for every individual suction pads. So this is just, you are distributing over your number of suction pads. So if you have many more suction pads, then the suction force that you need is less. But of course, many more suction pads, you can't just simply add as many as you want. There is a surface area limit as well. And at a certain point, additional pads don't help because they are outside of the surface area of the workpiece. So in our case, we are using 1822, which is the horizontal force and horizontal pad numbers. And according to this, if you have 6, then you need a diameter of 99 millimeters and suction force of 350 newtons. Okay, where you get this is basically from what we have already calculated, which is that we need this. Okay, and we need this. We get the force, and from this we can choose basically something that meets that. Okay, which is your PFYN 95 MBR. Okay, so from the technical data, we'll need 6 of them. Okay, so if we are looking for 80 millimeters, then we will need 8 of them in order to be able to meet our force for 1822. Okay, and once we have that, then we need to calculate what is it that the vacuum generator has to apply, which is basically what is the suction rate for each individual suction pad, and you multiply by the number of suction pads. Okay, this is not taking into account the design for the hosing and stuff. It's assumed that it's already done correctly. This is just how much volume flow for your suction needs to be done. Okay, and the final thing that we need to do is calculate what's the evacuation times. Basically, how long does it take in order to apply the vacuum? Because if that takes way too long, then that defeats the purpose. Okay, and for that, you need to look at basically all the different volumes that need to be evacuated, and these are provided in the specs. So basically, how much air volume there is inside the hose, depending on the length of the hose, how much air volume there is inside each suction pad. You have 6 suction pads, then you 6 times that volume. Okay, so that's why you see the 6 here. 6 times and 32 cm cube is the volume to be evacuated for the suction pad. Okay, so you add all of this, then you can calculate, okay, this is the total volume that you need to evacuate. Based on this total volume to be evacuated, then you take the natural log of the ratio between your start pressure, which is normally just our standard atmospheric pressure, and your final pressure, and you look at the suction rate of your vacuum generator. Then it says, okay, this is how much time, after all these calculations, this is how much time we need, 0.34 seconds to generate. This one is fine. If this calculation starts showing you, oh, I will need 7 seconds, depending on application, this could be too long. Okay, sorry, is there a question? Okay, if the formulas are required, then they are provided. Okay, there is no standard formula sheet for this subject, but if a question requires formulas, which are non-standard formulas, it will be provided. But you should not need a formula if you need things like rate, which is just something over time. If you need things like volume, which is just width times height times thickness. Okay, so those simple formula which you already know before you study degree, those cannot be provided. Will not be provided. I don't have infinite amount of paper to give you. But anything which is specific to our suction cups, okay, which is basically all these formulas on this that are shown on these slides, these will be provided if they are needed. Okay, so no need to worry about memorizing the formulas, but of course, provide the formula doesn't mean you know how to use it. So that our emphasis is on you being able to do, not so much on you being able to memorize. Okay, so I think, yep, that is done. Any questions?
So the 400 bar is where?
Say again?
How to 400 bar for the last slide?
Oh, the 400 bar is basically what we call 60%. If you go much earlier, I was saying that most of our applications are about 70%, 70% or 30% absolute. Okay, so basically that is the level of vacuum that you need for a particular application. Okay, in this application, it's not something that we calculate up. It's for this particular suction cup that we are going to use. For it to be active, you need about 400 millibar. Okay, so it's coming from the suction cup that we choose. Then we have this 400. Actually, what we have is 60%. We have this 60%, which means 400 millibar, and then we can plug it in there just to calculate the time.
So it depends on the
suction cup. Yeah, the type of cup, basically.
All right. Thank you, sir.
You are welcome. Any other questions? Okay. If no, then thank you very much. You may leave the meetings. I'll see you all again on Friday, unless our government suddenly decides to do some crazy things.